Today, we are here to talk about this quite an interesting topic that has been around in the buzz lately, what I would call it as electrochemical mileage demands. I just want to take a minute to describe this title, why it is so interesting before we actually understand what is all the buzz about lithium ion batteries these days. As we all know, batteries in general are electro and chemical systems, which provide us electricity because of chemical reactions within the cell. What I want to say is right now we are all driving towards an electric mobility, an electric way of going ahead for almost every single aspect of our life. And that is how I define a mileage in everybody's lives. And how much the demand is growing in every day is what we are trying to address and understand as a part of this webinar so that we can decide what is the future and what the future holds for us. And I would like to answer a question to see that our lithium ion batteries, which are the top rated electrochemical systems in the current generation, are they ready to power this mileage demands in our future? This will be the outline of the webinar today. We'll take a look at what are batteries in everyday life, what do we have them, and what are the present day rechargeable battery systems that are available for us, and how does the energy storage roadmap look like since the invention of the rechargeable technologies to what we have today to what we're going to see in the future. And after that, we're going to see a little bit about why lithium ion batteries are in so much demand. And once we understand what is the background, or why do we need such an understanding, we go into a little bit about the technology, a little bit of the chemistry, what powers the lithium ion batteries, what are the materials that go into different components of the battery that make the battery work the way it is. And then we'll understand a few challenges in operating these lithium ion batteries, followed by a very, very practical case study that I have in store for you towards the end of this presentation. And you have a lot of career and job opportunities in this area. I myself am a battery engineer by profession, and I have studied lithium ion batteries all through my undergrad, my post graduation. So I can vouch for you to say that this has a lot of opportunities in store. If you look at this batteries in everyday life, taking from as simple things as cell phones that you hold in your everyday pockets, in your everyday day-to-day lives, to all the way up to wind energies, electric vehicles, solar energies also, as we all know, they just don't come with the panels, but we have the power backup that we have to store that energy that the solar panels generate. The hydroelectric, anywhere there is a generation of electricity, you will need a storage because you can't use that electricity until you store it and then power the device in the way you want it. So from cell phones to laptops to drill bits to your camcorders or your mobile, any other portable communication devices, your e-readers, your tablets, wind energy, your storing of energy, batteries in literally every segment of our everyday life. If you look at present day rechargeable technologies, the most common technology that has come up even before lithium ion is the lead acid, and that has been the longest surviving rechargeable technology till today. Even the current petrol run or diesel run cars have a lead acid battery that you might all be aware of. Then comes the technology of nickel metal hydrides, nickel cadmium. These systems were earlier used in the first generation mobile phones and cordless electric phones. If you remember in early 1990s, we have the cordless phones and the mobile phones, which are really bulky. These are powered by nickel metal hydride. If you happen to open a particular one of these devices, you may have seen NIMH on the battery packs. That has developed and advanced into what we currently define as lithium ion. And this is where we are right now. So if you take a look at the graph here, that is just a basic schematic representation of how the technology has developed over time. What I try to project here is a power output versus what the energy is stored. And I'm sure most of you must have are aware of the terms power and energy. And for those of you who are not familiar completely, power is how much energy you can draw per time. So energy is the total energy that you can get out of the system, and power is how much you can draw per second. So you cannot have an energy storage device which can have extremely high power and extremely high energy. And for that, we need newer and newer technologies as we grow into to meet our energy requirements every day, the demand every day. And that is why, even right now, the lithium ion technology that we have today is not completely sufficient in itself. We are still searching for something that is more powerful. There's a high power lithium ions. We need high power in our life. And this is to give you a crude example or a crude day to day example of this power. It's basically the amount of boost that you get when you accelerate your electric vehicle. So if you press the accelerator on your electric vehicle, you want to hit from 0 to 100 kilometers per hour in less than 5 seconds. Now that is what I call high power. And for that, you need a high power energy storage device. In a lithium ion battery community, in generally a rechargeable battery community, what we define is we categorize the energy storage technologies in on the basis of their energy density in terms of their volume. So I call it watt hour per liter, and their energy density per weight, watt hour per kilogram. Now, this is important because we want to store as much energy as possible in a smaller volume, in a smaller space, and also at the same time make it as light as possible. So the quest is always towards going smaller in size and lighter in weight. So what we start off as lead acid, as I said in this plot as well, what we start off as lead acid has energy in the order of 100 watt hours per liter and a 50 watt hour per kilogram. So that means that if you want, if you take 1 liter, which is zero point 0.1 meter cube of a space, then you can only store 100 watt hours of lead acid energy. Whereas if you take the same space, you can almost store up to 400 watt hours in a lithium ion system. So basically, in the same space that you have, if you replace a lead acid with a lithium ion battery, then you're able to get more energy. And because of that, you're able to get drive range. If you want to translate it directly into an electric vehicle, or if you want to translate it to your cell phones, then it's more talk time, more hours of charge. You don't have to recharge it very often. So that is the advantage we are looking from going from lead acid systems to lithium ion. In between, you have the nickel metal hydrides, and then people are currently exploring what we call as lithium metal batteries. This is beyond the lithium ion that we usually talk about. So that is a little out of scope for this webinar, but to just give you an idea, this is currently under research, and it's right now, there are a lot of safety concerns with that technology. If you're interested, you can always Google it, and you will find lots of information on lithium metal batteries. Now, if you go if I just translate these two pictures into how the timeline of lithium ion battery has evolved, you can see that in 1990s, lithium ion batteries technology was so rudimentary, was so basic that we could not use them to power any extensive or bigger devices. It was limited to cellular phones, camcorders, and notebook PCs. So basically just phones and laptops. But the reason I chose 1990 as my start point is because that is the year where Sony commercialized its first lithium ion battery in the world for cell phones. And from then, people have accepted its efficiency. People have been impressed with what are the possibilities that you have with this technology. And with more and more advanced research, we are able to now go from just simple cell phones, small batteries, to power tools like drill bits. And then you have light motor vehicles uh, like two-wheelers, like bicycles. And then you're moving into electric vehicles, hybrid electric devices, and then grid storages. And by 2020, although Tesla has already been a little more aggressive, we are already by 2020, even before 2020, we have what is called Powerwall. And I'm sure most of you have heard about Tesla's Powerwall, which is basically a lithium ion battery powered inverter. And that has enormous amount of energy stored in one single block of battery pack that it can power your entire house for more than 24 hours. So if I go into the storage roadmap, these four pictures might be a little confusing over here, but I've pulled these images from different sources to make you understand what everybody predicts towards the maturity of lithium ion battery technology. And if you see here, this picture here is from US Department of Energy. And here they predict a roadmap from 2015 and beyond. And if you see here, at 2015, we are already reaching about 990 watt hour per kilogram or 3000 watt hour per liter. And if you imagine what I described in my previous slide, we are pushing from as much as 100 watt hours per liter in a lead acid system to as much as 3000 watt hour per liter. And that improvements in technology have made electric vehicles like Tesla or Nissan possible these days. And we are right now in the boom of going all electric. So with that background, I'm sure most of you are already excited about what is the technology and what makes these lithium ion batteries special. And this is just a very top level comparison of other parameters that we typically consider while designing a battery system for any specific application. As we know, we start with the energy density, and lead acid batteries are at 40 watt hour per kilogram or about 100 watt hour per liter. And as compared to lithium ion, which are about 95 to 140, which are right now, this is an older number. And today they are trying to push, theoretically, they're trying to push even up to 300 watt hour per kilogram on commercial battery systems. The slide that I showed in my previous, the figure that I showed in my previous slide is more at the research level. And when you commercialize it, you can achieve even up to 300 to 350 watt hour per kilograms. The charging efficiency, that is what I call as how much energy you put in while charging and how much energy you're able to take out during the discharge of these battery packs. So in lead acid systems, you can only utilize 70% of the total energy that you put inside the battery pack. And in lithium ion batteries, you can go up to 95%. Then charge discharge cycles. These are the cycles, the number of times you can charge and discharge the cell without it completely dying and completely unusable. Lead acid batteries only do give you 1200 cycles of charge and discharge, whereas lithium ion batteries go beyond 3000. Current technologies, if tailored specifically, can go even up to 5 or 6000 cycles. And in terms of emissions, there are a lot of gassing and water loss occurs when charging in lead acid batteries. Lithium ion batteries are emission free, and that's why we call them clean technology. There is no maintenance required in lithium ion batteries, and the best advantage of using lithium ion batteries is their fast charging capabilities. What I mean by fast charging is you can charge up to 90% of the battery pack in less than 2 hours. So that way, you do not have to spend a lot of time charging a battery pack. Rather than, you can discharge the same pack that you've charged in less than 2 hours for more than 10 hours. So that is the advantage you give. You charge for 2 hours and then you discharge it under 10 hours. Having said that, lithium ion batteries were not the first choice in the beginning of commercial energy storage devices. The reason being the cost of production of these battery packs initially were extremely high. back in 2005, you can see that the cost of production of these battery packs was as high as $1,300 US dollars per kilowatt hour. And with the advancements in technology, newer electrode materials, and newer and cheaper materials coming into uh, limelight, we are able to slowly control the cost and now bring it down all the way to about $200 per kilowatt hour. So in less than 10 years, we are able to reduce the the cost of manufacturing a lithium ion battery for electric vehicles specifically to almost a tenth of its value. And then the prediction is by the time we hit 2030, we are able to bring it down to less than 100 watt hour per kilo, $100 per kilowatt hour, excuse me. And that is the target that will get us close to manufacturing a petrol based car. So that is what we want to achieve to bring the manufacturing cost to less than $100 per kilowatt hour. And once we achieve that, lithium ions can extremely be economical, more economical than what we have right now. With that, there is some. This slide is going to show you some basic understanding of what lithium-ion battery chemistry looks like and how do you understand what happens inside a battery. I'm going to go a little deeper into the technology here. So we know a typical battery from high school physics and chemistry. We know that a typical battery consists of an anode and a cathode and what we call an insulating separator. So what I'll go with one by one. The separator, let's talk about that first because it looks like the most uh, non-participant component of the battery pack, but it is the most important because it electrically insulates both the active components of the battery pack. So separators are usually polymer-based systems which only let ions conduct between its pores. It's a porous polymer membrane, which is electronically insulating, but also at the same time ionically conducting. And then we have the electrolyte, which is an organic-based solvent-based system. So typically we have organic solvent, which is a carbonate, something like ethylene carbonate or ethylene methylene carbonate, something like that. And then we dissolve a lithium ion salt, which is typically lithium PF6 per hexafluorophosphate. And this solution is what people commercially use as in a lithium ion battery system or derivatives of the solution per se. Now we have for a battery to function, we have to have a lithium source and a lithium sink. And a cathode is typically called as a lithium source, which is typically a lithium-based oxide or a transition metal phosphate, one of those lithium-based compounds. And then an anode is a lithium ion acceptor, which is usually a carbon, silicon, or the future technology which I was talking about, lithium metal batteries, consist of lithium metal directly as an anode. So what happens when you charge a battery? If you look at this picture here, during charging, lithium ions go from the cathode to the anode. So they undergo a redox reaction in which lithium leaves the matrix of this compound. Let's say this is my starting material. Lithium leaves the matrix of this compound. It, it becomes lithium plus, and then it leaves out an extra electron. And that electron goes all the way in and from an external circuit to the anode. And then these lithium ions are conducted through the electrolyte to the anode. They absorb this electron from here, and then they reduce here to form something called lithium carbon compound. It's called lithium LiC6 or LiC2 as more and more lithium gets into the carbon matrix. So that's what happens during a charge. So what we call charge is during the charge, you have the cathode delithiating because it's losing lithium, and you have the anode lithiating because it's gaining lithium. And during discharge, the reverse happens. So when you draw power from the battery, your lithium ions are traveling from the anode to the cathode, and the current travels from the anode to the cathode from an external circuit. And that's what we call delithiation of the anode or the lithiation of the cathode. So what I show here is a typical charge discharge voltage profile in a lithium ion battery. So when someone talks about a lithium ion battery charging profile, this is the type of curve that you expect. It I mean, during the process of charging, the cathode undergoes an increase in its voltage, whereas the anode undergoes a decrease in its voltage because it's accepting lithium, it is its voltage decreases. And that's why you get a fully charged cell with a high voltage, which is defined as the difference between the cathode voltage and the anode. And when you discharge your cell, your cathode loses that voltage because it starts gaining lithium. And then your anode gains voltage because it's losing lithium. So whichever component gains lithium decreases its voltage. And during discharging, they both go towards each other. And that's when you have anode almost loses all the lithium and cathode gains almost all the lithium. Then we call that situation as a fully discharged battery pack. That is the theoretical part of the how a battery operates. But now we want to go into, in a commercial way, how do we charge and discharge a battery pack? Because a commercial cell usually consists of multiple charging stages. It's not just simple charge and discharge. We start with what is known as a pre-charge current. This pre-charge current is the current that we give. It's a very small amount of current that helps the lithium ion battery to condition itself, if that is one way of putting it. It will condition itself to reach to a point where we define as the voltage transition between the pre-charge and the fast charge. And then under this pre-charge region, you apply a very small current. And then we let the voltage of the lithium battery pack raise slowly. And once it hits this transition voltage, it enters into what is called as constant current mode. In the constant current mode, there is a very high current that is given to the battery pack. That is the current that we usually charge our cells with. And that's when you see the voltage increasing in the battery pack. And as the voltage increases, you see the percentage on your phone. Let's say you're charging your phone, then as the voltage of the battery pack is increasing, you see that the charging percentage goes higher up, and it goes into a point where we call constant voltage mode. And so this transition voltage, which is the regulation voltage, is what is that voltage which is written on the back of your battery pack. If your battery pack says rated at 4.2 volts, then this is that voltage that we are talking about. It goes in a constant current mode up to 4.2 volts, and then it stays at 4.2 volts for a good amount of time. This is what we call as a constant voltage mode. And at this voltage, it will stay until the total current of the battery reaches a certain value, which we call charge termination current. And this charge termination current is defined by if you let the if there is any residual lithium that is still yet to go into the carbon, then we will let that current that comes out because of this reactions is what we call constant current, like the charge termination current, this current that we're talking about. And when that happens, that is when we call the end of charge step. And the discharge happens according to however you pull the current out of the battery pack. So there are multiple stages in a commercial step, and all of these charging are different for different materials that you use inside the battery pack. So how you can charge a battery and how high of a voltage you can go in a battery pack, that's what I'm calling the rated voltage, is defined by how much, what kind of a material that you pick as your cathode and your anode. So here is a comprehensive list of all the materials that have ever been studied in literature, in research by various scientists all over the world, and have been summarized into one specific graph by this particular scientist, Jean-Marie Tarascon. And he claims that you have if you pick any material from this part of the plot, if you see that, that is the voltage of the material. So every material has a voltage that you can define with respect to lithium metal. So when I say voltage of LiMnO4, I'm saying that it is with if I say that is 4.2 volts, I'm saying that that voltage is versus lithium metal. Lithium metal over here, it's considered to have a standard reference voltage of 0 volts. So when I say that I mean, this particular material has 4.2 volts, yes, it is 4.2 volts with respect to lithium metal. And similarly, we have a list of negative materials, which we call anodes, and these materials do not have lithium. If you've observed, negative materials are lithium ion acceptors, and so they do not have lithium metals inside their system. They only the positive materials have lithium metals inside their systems. And so we commercially use graphite as a negative ion, negative material. So if you look at it, graphite is used because it has a potential that is very close to lithium metal. It's very close to 0 volts. So your lithium ion acceptor must be as close as possible to your lithium metal, and lithium ion source, which is the positive material, should be as high up away from the material, away from lithium metal as possible. So the most ideal situation would be to have a material that is much higher up here, which is paired with an anode which is as close as possible to lithium metal. And that is why we pick in commercial systems, in all electric vehicles and all consumer electronics systems, we pick lithium cobalt oxide as our most common cathode material and graphite as the most common anode material.